There's a video of Keith Jarrett, who's a well-known jazz improviser and probably the most well-known, iconic example of someone who takes improvisation to a really higher level. And he'll improvise entire concerts off the top of his head, and he'll never play it exactly the same way again. And so as a form of intense creativity, I think this is a great example. And so why don't we go ahead and click the video. Truly, we know very little about how we are able to be creative. And so I think that we're going to see over the next 10, 20, 30 years a real science of creativity that's burgeoning and is going to flourish because we now have new methods that can enable us to take this process of something like this, complex jazz improvisation, and study it rigorously. And so it gets down to the brain. And so all of us have this remarkable brain which is poorly understood, to say the least. I think that neuroscientists have much more questions than answers, and I myself, I'm not going to give you many answers today, just ask a lot of questions. And fundamentally, that's what I do in my lab. I ask questions about what is this brain doing to enable us to do this. This is the main method that I use. This is called functional MRI. If you've been in an MRI scanner, it's very much the same, but this one is outfitted in a special way to not just take pictures of your brain, but to also take pictures of active areas of the brain. Now, the way that's done is by the following. There's something called bold imaging, which is blood oxygen level dependent imaging. Now, when you're in an fMRI scanner, you're in a big magnet that's aligning your molecules in certain areas. When an area of the brain is active, meaning a neural area is active, it gets blood flow shunted to that area. That blood flow causes an increase in local blood to that area with a deoxyhemoglobin change in concentration. Deoxyhemoglobin can be detected by MRI, whereas oxyhemoglobin can't. So through this sort of method of inference, and we're measuring blood flow, not neural activity, we say that an area of the brain that's getting more blood was active during a particular task. And that's sort of the crux of how fMRI works. And it's been used since the 90s to study really complex processes. Now, I'm going to review a study that I did, which was really jazz in an fMRI scanner. You can't just sort of, it's great, we got this keyboard. We actually have to come with a scientific experiment. And so the experiment really rests on the following. What happens in the brain during something that's memorized and overlearned, and what happens in the brain during something that is spontaneously generated or improvised in a way that's matched motorically and in terms of lower level sensory motor features. And so I have here what we call the paradigms. There's a scale paradigm, which is just playing a scale up and down memorized, and then there's improvising on a scale, quarter notes, metronome, right hand. Scientifically very safe, but musically really boring. And then there's the bottom one, which is called the jazz paradigm. And so what we did was we brought professional jazz players to the NIH, and we had them memorize this piece of music on the left, the lower left, which is what you heard me playing. And then we had them improvise to the same exact chord changes. And if you could hit that lower right sound icon, that's an example of what was recorded in the scanner. So in the end, it's not the most natural environment, but they're able to play real music. And I've listened to that solo 200 times, and I still like it. And so, the musicians they were comfortable in the end. And so we first measured the number of notes. Were they in fact just playing a lot of more notes when they were improvising? That was not what was going on. And then we looked at the brain activity. I'm going to try to condense this for you. These are contrast maps that are showing subtractions between what changes when you're improvising versus when you're doing something memorized. In red is area that's active in the prefrontal cortex, frontal lobe of the brain. And in blue, this area that was deactivated. And so we had this focal area called the medial prefrontal cortex that went way up in activity. We had this broad patch of area called the lateral prefrontal cortex that went way down in activity. I'll summarize that for you here. Now, these are multifunctional areas of the brain. As I like to say, these are not the jazz areas of the brain. Right? They do a whole host of things that have to do with self-reflection, introspection, working memory, and so forth. Really, consciousness is seated in the frontal lobe. But we have this combination of an area that's thought to be involved in self-monitoring turning off, and this area that's thought to be autobiographical or self-expressive turning on. And we think, at least in this preliminary, it's one study, it's probably wrong, but it's one study, we think that at least a reasonable hypothesis is that to be creative, you have to have this weird dissociation in your frontal lobe. One area turns on, and a big area shuts off so that you're not inhibited, so that you're willing to make mistakes, so that you're not constantly shutting down all of these